Okay, I'm going to do a couple extra examples here. First off, we're going to go back to section 9.2, and I'm going to do an example involving mass. So we have this assembly, and it's made out of a hemisphere with a cylinder on top. The hemisphere is made out of steel, and the cylinder is made out of aluminum. We're given the mass for the hemisphere, but since we don't know what height this shaft is going to be, we only have the density for it. So what we need to do here is we need to determine z bar. So z bar is essentially the sum of our z alphas times the mass divided by our sum of masses. So we only have two different materials here, so we're going to have a z alpha 1 and a mass 1 plus a z alpha 2 and a mass 2. And then we're just going to sum the two masses, mass 1 plus mass 2. And that's simply all we're going to do. So let us begin here then. So mass 1, let's call this our steel hemisphere, is 0.06691. And then the z bar to that it's going to be somewhere down here, I think. If you look at a hemisphere, it's usually measured from the other direction. Usually, if you look in your book, it's usually measured from this direction. So what I'm going to have to do is I'm going to have to take the total distance and subtract that off. So I'm going to go 0. Oops, I don't want to be the big color. 0.16 meters, and then I'm going to subtract off what the distance is from the top surface to the centroid of that hemisphere. Okay, so that's the first term, and then we got the z bar to the second term, which is going to be the distance here plus half the distance to the whatever h is, and we don't know what h is. Okay, and then for the mass, so this is mass 1, this is z alpha 1, and then I kind of reverse things here. This is z alpha 2, and this will be mass 2. So the mass here is going to be, well, we'll just calculate the volume of this cylinder and then multiply it by our density. So our density is 2.7, and that is in meters cubed. 2.7 times pi h times r squared, which is 0.8 squared. Have to convert everything to meters here. And there we go. So that's the numerator. And we can divide this by then the denominator. So we've got 0.06691 plus, well, this is going to turn out to be, the mass 2 is going to turn out to be, I may as well write it here, 0.05429 times whatever h is. Okay, that's an equation, and we could just manipulate that equation if we needed to find anything out. Let me simplify it though. So this is, so now I've written it in a simplified form and wrote it as z bar of h. So that's the distance z bar as a function of h. So all we can do is we can stick in h's here and calculate then what our z bar is once we figure out what our h's are. So suppose we want to calculate z bar of h of 200 millimeters or 0.2 meters. That's going to equal. So I'm going to go ahead and put this in a little math program as opposed to a calculator. You can type it in your calculator if you want. And I'll hit equal, and I get z bar equals 0.122. That sounds good. So that's 122 millimeters then. So it looks like it's down here somewhere. Okay, so that's where it is. Now, let's say I want to find h now up here in such a way that my z bar is 160 millimeters, right at the edge of those two. So I can use this equation to do that, and what I'll want to do then is, you could trial and error, but we don't need to do that. We'll go ahead and use a solver. So here's the script I wrote. First I clear my screen, then I clear my workspace, and then I have this command line. And I write my function. You got to make sure that this is actually one line, not two lines like this. Okay, and then here's my result. So we get two answers. We get this guy and we get this guy. I'm just going to disregard this guy. And we should expect to get two answers because this is a quadratic equation. And so the answer is then that h is 0.385 or approximately 385 millimeters. Okay, so just a quick little thing to show you how to do maybe a parametric study on this if you had to called on to do something like that in the lab you were working at or something. Okay, next I want to solve this problem, and the first thing I'm going to do is I like to always calculate the area. Let me write down what this is though. X bar is going to be the integral of our x tilde dA over the integral of dA. So let's figure out what the area is. It's the integral of dA first. So as we look at this, we see that this is a little wedge here, and what it really is going to result in for us is what we'll do is we'll figure out the integral of this first, which is going to give us the area of this triangle, and then we'll figure out the integral of this function shape, so it's the area underneath that function then, and we're going to subtract that from the first one. So it looks something like this. So the integral from 0 to 100 of x dx. I'm writing this in terms of x. We could really say this is y, f of x dx, but f of x equals x. So I'm just shortcutting that, and we're going to then subtract off the integral from 0 to 100 of f of x again, which is 1 over 100 x squared dx. So we can combine this. Integral 0 to 100 of x minus 1 over 100 x squared dx. Pretty simple integral to do. So again, what that is we're taking this triangle that we calculated here, we're subtracting off this. So you have to understand how your integration works. We're subtracting off this area because what we need is everything in between this area. So this now is x squared over 2 minus 1 over 100 x cubed over 3, evaluated from 0 to 100. This is going to turn out to be 10,000 over 2 minus 10,000 over 3, which ends up being 5,000 over 3. Let's just keep it like that. Okay, now that I'm comfortable calculating that area, let's expand it to x bar, which is going to be the integral of our... So we're going to take x and multiply it by the function that we had before, x minus 1 over 100 x squared dx, and of course this whole thing is divided by the 5,000 over 3 that we calculated already. So again, we'll simplify this. So we're going from 0 to 100 here. So we're going from here to here with our integration. So this is x squared minus 1 over 100 x cubed dx, still divided by 5,000 over 3. Okay, well this is going to be x cubed over 3 minus 1 over 100. So this is going to turn into an x to the 4th over 4, which will evaluate from 0 to 100. And then this is going to end up being 100 cubed over 3 minus 100 cubed over 4 divided by, oops, we forgot to put this here, 5,000 over 3 divided by 5,000 over 3. And this is like 250 thousands. It's just dealing with zeros here. Over 3, 5,000 over 3. Simplifying these fractions, so we can get rid of the 3's and we can get rid of 3 zeros essentially. 3 zeros gone, 3's are gone. So we've got 250 over 5, which is 50 millimeters. That's our answer. So now with y bar, we're going to do y. Well, the thing is we're going to be integrating this way now with y, and we need to find these are one-to-one relationships here on these functions. We need to invert these so we get functions. We get x as a function of y. And so that's that. So this is like 10 square root of y. And here now when we do this, our first area will be this. And then we will subtract off this. So I suggest you calculate the area first and make sure it comes out to 5,000 over 3. So again, here we are setting this up. We've got this minus this is going to give us this. And that's actually for the area, but I'm going to multiply each of these by a y. So I got a little ahead of myself back there. So this is the area then, and we'll calculate this. Then if I want to calculate y bar, I'll multiply all this by y. I'll then integrate this numerator, then simplify this, as, do some cancellation here, get rid of those, get rid of that, get rid of that, and we come up with 40 millimeters as our result.